Okay, the first speaker is Mamoru Matsuo, and he's telling us about spin transport in condensed matter physics. So please start.
Okay, thank you. First of all, I'd like to thank to the organizers for giving me this nice opportunity. And today, I'd like to talk about the spin transport via the spin vortice decoupling in the condensed matter physics. And I'm very happy to be here because our theoretical prediction done in collaboration with Professor Mike Howard of the JEA very nicely demonstrated by the experimentally in the collaboration with the experimental group of the Professor A.G. Saito's group of the JEA and Professor Hiro Nozaki's group of the Keio University and the Professor Hirohata's group in the York University. Okay, so today I'd like to focus on the spin manipulation via the spin vortice decoupling. The conventional spintronics utilize the exchange coupling and spin orbit coupling to manipulate the spins. So, which means if you manipulate the spins, you need the magnets or the strong spin orbit materials such as the platinum or the tungstens. I mean the heavy metals. But if you use the spin vortice decoupling, we don't need any magnets or the strong spin orbit materials. So this new mechanism give rise to the new spintronics devices using the small spin orbit coupling materials. Okay, this is our ideas. So this is the outline of my talk. First, I'd like to show you our recent a new type of the Barnett effect. And the second part, I'd like to talk about the spin transport driven by the spin vortice decoupling. Okay, so let's move on to the first part. Okay, so this animation shows the Barnett effect, the magnetization by rotation, and we have the a classical analog of this Barnett effect, the gyro effect. You can manipulate the spinning object by applying the external mechanical rotation. And this manipulation can be realized by using the coupling between the mechanical angular momentum L and the angular velocity omega. And very similarly, in the materials, we have the spin rotation coupling. And by using this coupling, we can manipulate the magnetization by using the external rotation. And this coupling is very simple and very similar to this, but the very non-trivial coupling. So today I'd like to skip the detail of the origin of the spin vortice decoupling, but if you understand this mechanism, this origin, we need the tetrad formalism for the describing the generally covariant Dirac-Lagrangian, which is given by in this form. And very similar to the U1 gauge coupling, the spin current is coupled to the spin current coupled to the gravitational field, which is given by described by the spin connection, kind of the twist of the tetrads. And this Lagrangian has a local SO31 gauge symmetry, which assures the angular momentum conservation law. And from this interaction term, we have the spin vortice decoupling. Okay, this is the mechanism of the origin. And today, I like to show you the typical, the following three type of the rotation or the vorticity sources as a kind of the magnetic field. the spin rotation coupling or the spin vorticity coupling can be interpreted as a coupling between spin and magnetic field, which is given by the omega divided by the gamma. Gamma is the gyromagnetic ratio. So the important point here is rotation is a kind of magnetic field. And if you use the rigid rotation, we can access by using the ultra high speed rotor, we can access up to the 10 kilohertz frequency regime, and which corresponds to the 1 micro Tesla magnetic field. Okay, and in the case of the vorticity field created in the liquid metal pipe flow, the rotation frequency is about to the 1 kilohertz. And also, we can use the vorticity field created by using the surface acoustic wave. And in this case, we can use the several kilo gigahertz region. But this magnetic field is an AC magnetic field. So now let's move on to the first topic. So now let's consider how to detect directly the spin rotation coupling. Okay, so the spin, as I told previously, the spin rotation coupling is a kind of the Zeeman coupling. And this effective magnetic field is proportional to the mass. So the magnetic field acts on the nuclear spin is much larger than the magnetic field acts on the electron spins. Okay. So we consider we can directly detect the spin rotation coupling by using the NMR. Okay, so this is the cartoon of the conventional NMR spectrometer. If you apply the external magnetic field B0, then the NMR resonance condition is given by in this form. But if you use the rotating observer, I mean the spinning NMR spectrometer, then this the split due to the Zeeman coupling is the more the splitted by due to the spin rotation coupling. So in such a rotating observer, the NMR frequency condition is shifted due to the spin rotation coupling. But the problem here is how to prepare the rotating observer. But because if you use the wired circuit, you cannot rotate this spectrometer. So our collaborator, Dr. Chudo, developed the new experimental method, as like this. So by using this new method, the spinning NMR in the absence of the spin rotation coupling is shifted due to the spin rotation coupling. And the very interesting point here is the nuclear spin. Some nuclear spin has the positive gyromagnetic ratio, and the other have the negative gyromagnetic ratio, which means the frequency shift due to the spin rotation coupling for the positive gyromagnetic ratio or materials is the and in the case for the negative gyromagnetic ratio, the sign of the frequency shift is the opposite way. So we can as you can see here, such behavior due to the sign of the gyromagnetic ratio of the nuclear can be observed by using this Dr. Chudo's technique. And also we developed the in situ high sensitive measurement And from this new technique, our collaborator observed the Barnett effect in the paramagnetic states material. So the originally Barnett used the ferromagnet, but in our case, the Barnett to observe the Barnett effect in the paramagnetic state, we need the in situ high sensitive magnetic field measurement because the magnetization by rotation in the paramagnetic state disappears when you switch off the mechanical rotation. So we developed Dr. Ono developed the new technique which measures the tiny straight field, straight magnetic field due to the paramagnetic Barnett effect by using the flask scale sensor. Okay, so the very interesting application of our Barnett effect measurement is as shown here. Okay, so as I said, the mechanical rotation is a kind of magnetic field, but this is not identical because the magnetic field coupled to the magnetic moment like this, but the mechanical rotation couplings to the total angular momentum. So the slightly different of these two couplings. So if you consider the ferrimagnets, ferrimagnets consists of the two magnetic moments, A sublattice and B sublattice, and generally these two sublattices has the different temperature dependence. And now let's consider the AA coupling is the ferromagnetic interaction, and BB also the ferromagnetic, but the AB coupling is the anti-ferromagnetic. If you use such a kind of coupling, we have the very interesting the compensation points. First, two compensation points. First one is the magnetization compensation point, and the other is the angular momentum conservation point. Because this figure shows the temperature dependence of the magnetization for the A sublattice and B sublattice, like this. So due to the different temperature dependencies, we have the total angular momentum vanishes in this temperature. And this is the magnetization compensation point. And now let's look at the angular momentum, temperature dependence of the angular momentum. The angular momentum is given by the magnetization divided by the G factor. And if we choose the material for the this kind of condition for the G factor, then this dotted line indicates the temperature dependence of the angular momentum for A sublattice, and this dotted line indicates the B sublattice. So the difference, due to the difference of the G factors, the this point is the total angular moment vanishes. This is the angular momentum conservation compensation point. Okay, so these two temperatures are different. Okay, so now this is the our result. The upper panel shows the magnetization compensation temperature measured by the magnetic field responses. Okay, but due to our new technique, we can access the angular momentum conservation temperature shown in this point. Okay, so this is a very interesting demonstration of the application of the Barnett effect. And so because this angular momentum compensation temperature is very important to the magnetic devices. Okay. Okay, so and very recently we have the very a new type of the Barnett effect. So we use the spin vorticity coupling driven by the Rayleigh type surface acoustic wave in the ferromagnetic thin film. And these arrows indicates the vorticity dynamics of the vorticity field. So as you can see here, these vorticity field is the AC and the non-uniform, especially non-uniform vorticity field. By using this, and we tune the frequency to the ferromagnetic resonance condition, then we can demonstrate the gyromagnetic effect can be utilized to excite the spin wave propagation. Okay. So now let's move on to the second topic, second part, the spin transport by using the mechanical rotation or the vorticity field. Okay. So now let's start with the Dirac Hamiltonian in the rotating frame. This Dirac Hamiltonian is has the two different terms, has the two additional terms compared to the usual Dirac equation here and here. And this is the omega cross r is the rotation velocity. So as you know, the velocity operator for the Dirac spinner is the C alpha. So this velocity operator is shifted to the mechanical rotation or omega cross r, and also the energy shift due to the spin rotation coupling is given in this form. Okay, so from this Dirac Hamiltonian, and by using the non-relativistic approximation, we obtain the Pauli equation in a rotating frame in the presence of the electric field and the magnetic field. So this term is nothing but the spin rotation coupling. But very interestingly, up to the order of the 1 over m squared, the spin in orbit coupling is modified in this way. So the electric field appeared in the spin orbit coupling is shifted by this kind of effective electric field given by the omega cross r cross b. Okay, so this is the V. This form is very similar to the V cross B term. Okay, and also the Zeeman coupling is shifted by the spin rotation coupling. Okay, so we can consider the new two type of the new mechanism for the spin current generation. First one is by using this mechanical induced spin orbit coupling. We can predict the new kind of the spin Hall effect by using the rotation and magnetic field. Okay. And also another type of the spin current generation can be considered by using a mechanical analog, the Stern-Gerlach effect driven by the vorticity gradient. Okay, so let us look at this first mechanism. Okay, so this animation is the spin, the situation for the conventional spin Hall effect. Okay, if you have the spin orbit coupling S dot P cross E, you can calculate the spin-dependent velocity operator, which is given by the commutator of the R and the spin orbit coupling, and then we obtain the S cross E is electric field. So which means if you apply the charge current in this direction, then up due to the spin-dependent velocity term, the up spin goes to this way and down spin in a down way. So which means the longitudinal charge current is converted into the transverse spin current. This is the spin Hall effect. Also, we have the reciprocal process of the spin Hall effect, which so-called the inverse spin Hall effect. And the inverse spin Hall effect is utilized for the detection of the spin current by the electric voltage. So analogically, in our new spin orbit interaction term, the S dot P cross and omega cross R cross B, this is the ineffective field created by using the coexistence of the mechanical rotation and the magnetism. Then if you apply the magnetic field parallel to the mechanical rotation axis, then this omega cross R cross B field is created in the radial direction. So the radial in the radial direction, the radial charge current can be in this situation due to this mechanical spin orbit coupling. The radial charge current is converted into the this kind of circular motion of the spin current. Okay, this is the new type of the spin orbit spin Hall effect. And very recently, Professor Hirohata's group demonstrated by this mechanical induced the spin Hall effect by using the magneto-optical detection method for the platinum and the tungsten. And in this mechanism, we need the strong spin orbit coupling, also the magnetic field. But in the following, we consider the purely the mechanical origin of the spin current generation. Okay, so and in this case, we consider we analyze the coupled equation of the spin diffusion for the electron spins and fluid or the elastic motion for the lattice. Okay, and these are the coupled equation in the presence of the spin vorticity coupling. Okay, and in the presence of the spin vorticity coupling, the spin diffusion equation is modified in this way. And in the left-hand side, we have the two different kind of the source term coming from the lattice or the fluid vorticity motion. And also the fluid elastic equation is modified by introducing the anti-symmetric stress tensor, which includes the rotational viscosity. Okay. So now let's look at this spin diffusion equation. Okay, and in particular, this spin diffusion equation in the presence of the spin vorticity coupling can be derived by using the non-equilibrium Green's function method, and the detail of the derivation. I'd like to skip the details of the derivations, but we use the relaxation time approximation of the for the Kadanoff-Boehm equations collision term. Okay, and now in the coarse graining procedure, we have the conversion efficiency parameter zeta. in this form, then the which denotes the indicates that the conversion angular momentum conversion efficiency from the vorticity field to the electron spins. And this number of the conversion efficiency is determined by the difference of the two time scales, namely the one is the electron spins relaxation time, which is the about to the picosecond scale, and also the time scale of the vorticity field, and in the case for the elastic motion, the vorticity time scale for the vorticity field is about to the nanoscale, and the vorticity time scale of the vorticity for the fluid liquid metal pipe flow case, the millisecond, and this the big difference causes that the big difference of the conversion efficiency theta, because because the usually the two different modes are easily coupled in the case of the small difference of the time scales. So in our case, the elastic time scale for the elastic motion is the much large, much faster than the fluid motion, and so the in the case of the conversion, angular momentum conversion from the elastic motion to the electron spin is much larger than that for the fluid motion. Okay. And this is the theoretical prediction, but actually, very recently, Professor Nozaki's group demonstrated this big difference in the case for the elastic by using the surface acoustic wave. So and now let's look at the fluid elastic equation. Usually, for instance, the Navier-Stokes equation is nothing but this part. But in our case, in the presence of the spin vorticity coupling, we consider the linear momentum as well as the angular momentum of the fluid element, which means we must introduce the anti-symmetric part of the stress tensor, which describe the relaxation of the vorticity to the spinning motion of the fluid element to the vorticity field. Okay, so as a result of the introducing the anti-symmetric part of the stress tensor, the Navier-Stokes equation is modified as like this, and also the elastic equation is similarly modified as this. And an important point here is the usual viscosity term is enhanced due to the rotational viscosity in the presence of the spin vorticity coupling. And also that we have the additional term which describe the back action from the electron spin to the mechanical motion. Okay. So our collaborator demonstrated that this kind of the back action by using the micro ferromagnetic cantilever. So they inject the spin current into the ferromagnet cantilever, then they excite the bending motion of the cantilever due to the back action term via the spin vorticity coupling. Okay, and now let me show you the spin current generation by using the pipe flow of the liquid metal. Okay, this is the experimental setup. I think that this is the one of the most simplest setup published in the Nature Physics paper. We think we prepare the quartz pipe, and we put the voltmeter in this way. So and we put the gallium alloy and or the liquid mercury metal put into the this quartz pipe, and then we apply the pressure, then we generate the pipe flow. Okay. And in this pipe flow, now let's look at the cross section of the pipe flow, and we in this case, we have the vorticity gradient in the radial direction of the pipe flow. Okay, because the near in the vicinity of the edge, due to the friction between the inner wall and the liquid metal, then the fluid velocity is very small in the vicinity of the inner wall. But at the center of the pipe, the velocity flow becomes the maximum. Then we obtain the vorticity gradient in this way. Okay, so this due to this vorticity gradient field, the spin current is generated in the radial direction, and this is the mechanism of the spin current generation. But additionally, we have also the inverse spin Hall effect in the due to the spin orbit coupling of the liquid metal. Okay, due to the spin orbit coupling of the liquid metal, this generated spin current can be converted into the electric current in the pipe flow. Due to the along to the pipe flow. Okay, so you can this technique is the typical. This is the typical electric detection technique for the spin current generation. Usually, you put the heavy metal such as the platinum to the spin current source. But in this case, our spin liquid metal is a spin current source as well as the spin conversion detection materials from the spin current to the electric current. So that's why we can easily access the spin current generation by detect this electric voltage in this direction. Okay, so and also very interestingly, our collaborator demonstrate the very different behavior, scaling behavior for the electric voltage. Okay, this two graph shows that the electric voltage signal is proportional to the square of the averaged flow velocity for the turbulent flow. But in the laminar flow case, the electric voltage is proportional to the flow velocity. Okay, so these results are very good agreement with the theoretical prediction. Okay. And this is the our collaborators, our group's data, but you can see also very recently, the for Gallenstein case, the German group also demonstrated this kind of the scaling behavior. Okay, so we discover the big difference of the conversion efficiency of the from the vorticity to the spin current in the case of the laminar flow and the turbulent flow. Okay, so in the laminar flow case is much larger than that for the turbulent flow case, because in the laminar flow we have the vorticity gradient is created all over the cross section of the channel. On the contrary, in the turbulent flow case, the vorticity gradient is localized near the wall. Okay. That's why these difference shows give us the big difference of the conversion efficiency. Okay. So now, let me show you the another mechanism of the mechanical analog of the Stern-Gerlach effect driven by the spin vorticity coupling by using the Rayleigh type surface acoustic wave. Okay, previously I also showed a very similar situation for the Barnett effect driven. We demonstrate the Barnett effect can excite the spin wave propagation. But in this case, we use the non-magnetic material, copper. Okay, and conventionally, the copper is not considered as a good spin current source because the copper's spin orbit coupling is very small, which means that we don't have the we just have the very, very small spin in Hall effect, which means the copper is the not good material for the spin current source. But if you use our new mechanism driven by the spin vorticity coupling, the copper becomes a very nice spin current source. Okay, this is the snapshot of the this animation. Okay, and as shown here, and we have the vorticity gradient due to the Rayleigh type surface acoustic wave in this direction, which means the spin current is generated along in this vorticity gradient. But as you can see here, this vorticity field is the AC and also the spatially non-uniform. So the generated spin current is AC and also the non-uniform spin current. So which means we cannot access the spin current by using the inverse spin Hall effect, because conventionally the spin current, DC spin current can be detected by using the inverse spin Hall effect. For instance, you put the platinum film onto the spin current source and you measure the electric voltage, then the generated spin current is injected into the platinum film, and in the platinum film, the injected spin current is converted into the transverse electric charge current. But in our case, this generated spin current is non-uniform, which means the electric voltage is compensated. So we cannot use the conventional method to detect the AC spin current. So but Professor Nozaki of the Keio University got the very nice idea to detect the AC spin current. He used the ferromagnetic film to detect the AC spin current. Okay, and this is the setup. This copper layer is the spin current source. So, and he put the ferromagnetic metallic film onto the copper layer. So now you apply the surface acoustic wave. Then in the copper layer, we obtain the spin current, AC spin current generation, and the generated AC spin current injected into the ferromagnetic thin film. Then this spin current leads to the torque onto the magnetization in the ferromagnetic thin film. Then if you choose the frequency of the surface acoustic wave to the ferromagnetic resonance condition of the ferromagnetic thin film, then we obtain the spin wave excitation. And in such situation, we have the attenuation of the amplitude of the surface acoustic wave due to the microwave excitation driven by the AC spin current torque. Okay, this is the a very nice idea of the.
Mamoru, so you have 5 minutes.
Oh, thank you. This is the experimental results. This barrier system, we have the clearly clear signal of the microwave absorption due to the spin current generation. And if you block the spin current injection from the copper layer to the ferromagnetic thin film by using the this silicon oxide film, then this microwave of absorption disappears. And of course, for the permanent monolayer ferromagnetic monolayer film, we have the almost nothing. Okay. So that this is the demonstration of the spin current generation via the spin vorticity coupling. Okay. So now finally, I'd like to show you the very interesting spin current generation. The previously we used the moving material such as the rigid rotational motion and or the elastic motion and the fluid motion, but to obtain the vorticity field, we can prepare the non-moving material such as the surface oxide copper thin film. Okay, so this gradient material, we have the non-uniform electric conductivity, which means if you apply the electric field in this way, then we can generate the non-uniform charge current as shown here. So in this situation, we have the vorticity gradient in this direction. So due to the this non-uniformity, the spin current is generated in this direction. But very interestingly, these spin vorticity coupling appears only when you switch on the charge electric voltage in this direction. So if you consider the inverse process of this, I mean that if you inject that spin current in this direction, nothing happens because in this situation, we have the no vorticity field because in the absence of the because of the absence of the electric field or the no non-uniform electric electric charge current configuration. Okay, so this result shows the big difference between the conversion efficiency from the charge current to the spin current indicated at this point, and this point is for the conversion efficiency from the spin current to the charge current. Okay, this is very, very different from the conventional spin Hall effect and the inverse spin Hall effect. In such case, we use the both processes. We use this spin orbit coupling. So always exists in this process and this process, but in the case for the gradient material, we have the very big non-reciprocal phenomena for the spin to charge conversion efficiency. Okay. So now let me summarize my talk today. I present the two phenomena. The one is the Barnett effect, driven by the nucleus spin vortice decoupling, and such spin vorticial spin rotation coupling is directly observed by using the spinning NMR, and also the in situ high sensitive measurement technique. We demonstrated the very interesting behavior of the ferrimagnets, and also the surface acoustic wave driven by the new kind of the gyromagnetic ratio. And the second part, I show you the spin transport driven by the mechanical spin Hall effect, which is detected by the magneto-optical detection method, and also the spin current generation by using the vorticity gradient in the liquid metal flow and the surface acoustic wave, and also the non-moving material of the gradient material. Okay, thanks so much for your attention.
Okay, thank you very much for such a nice, very informative talk. And now the question. Okay, Jojo.
Hi, thank you for, this was a really, really great, really informative talk. Let me ask you one thing. I was interested in this turbulent versus laminar flow.
Mm-hmm.
Can you take this, arrange a situation where viscosity is as low as possible, but polarization is non-zero? So a significant amount of angular momentum is carried by viscosity. A significant amount of angular momentum is carried by spin. So polarization is non-zero, but viscosity is close to zero as possible. Can you see something like polarization giving you an effective viscosity? Maybe turbulence goes into it as well, but just wanted to ask.
So sorry, I couldn't catch your point. You like to consider the spin polarization, the difference between the for the turbulent case and the laminar flow case. No.
Yeah.
Yeah, actually, in our phenomenological model, we use the very, very phenomenological simple model for the turbulent case. So that just we must restrict ourselves to the very, very simple argument in our case. So sorry for the I couldn't any detail or the more microscopic mechanism for the turbulent case.
No.
No.
I wasn't asking for microscopic microscopic mechanism for turbulence.
Mm-hmm.
What is interesting is what happens if viscosity goes to zero in this fluid. It's impossible to avoid a turbulence phase, right?
Yeah.
Yeah. I will give a talk. I will give a talk soon. And I will talk about the relation between polarization and viscosity, that at least relativistically, polarization should give you some measure of viscosity. It's a relativistic statement. But because of this, I was just interested if you could take the viscosity to zero.
But in this case, the viscosity is not changed, but the system size is changed to change the Reynolds number, right?
Yeah.
Okay, so that is a comment. Okay, so let's go to the next question. So Oleg, please.
Thanks. I have a question to the slide number 13. It was also discussed later that the frequency of rotation of spin is equal to frequency of orbital momentum. And in fact, as spin is quantum, it is a manifestation of the equivalence principle, of post-Newtonian equivalence principle. And I would like to ask, what is the accuracy to which it is tested now? Because say from electric dipole moment experiments, the accuracy is about 1% or so. So what is the accuracy to which is now known that the precession frequency of spin coincides with precession frequency of orbital momentum? Just the blue equation.
Blue equation.
Blue, he just on blue equation on page 15, where two frequencies are equal, L plus S. So it is to which accuracy it's now tested.
This L plus S?
Yes, yes. What is the just accuracy of the test of this combination?
Accuracy.
Yes.
Within the within the experimental demonstration, this is a very accurate expression. But so the L plus S is a very accurate so far in our experimental demonstration.
Just I would like to point the attention to attract the attention to the fact that it is also, it seems trivial, but it is also a test of equivalence principle for spin. So then the accuracy is maybe important.
So your question is that's very fundamental physics.
Yeah, but because it's known that that spin rotates with the same frequency as orbital momentum, it is known to be the manifestation of equivalence principle, and the equivalence principle for free fall is tested to very high accuracy. So here the accuracy may be important. So this is what I would like to.
But so far, our experimental accuracy is very limited. For instance, for the gyromagnetic radiation measurement, we just have this number. So
I see. So maybe currently the accuracy of just electric dipole moment type experiments is high, but maybe in future condensed matter can be can be stronger.
I think that to answer your question, we must have the very fancy setup, for instance, the quantum spin system or the I guess so. We just have the very common material. So
I see.
Our system is a very kind of the dirty system.
I see. Thanks.
Thank you.
So okay, let's go to the next question. Shugan, please.
Yes. Hi, Mamoru. Thanks for the very interesting talk. I have 4 very short questions.
Okay.
The first one is that you mentioned that there are some material whose zero magnetic ratio is positive, and there are also materials whose general magnetic ratio is negative. Then what determines the sign of the this zero magnetic ratio, or which material?
This is coming from the neutron magnetic moment and the proton magnetic moment. This magnetic moment, the sign of the magnetic moment is the opposite. So the composite number of the neutron spin and the proton spin give rise to the such difference of the sign for the gyromagnetic ratio. But the detailed discussion is more complicated, I think.
Okay, I see. Okay. Okay, thank you. The second question is on page 22.
22, okay.
Page 22.
22?
Oh, right.
Okay.
In the first equation, right? In the first equation on the right-hand side, why you don't have the zeta coefficient for the first term?
This is the origin is different because today I don't have the additional backup slide, but this first term is coming from the Brasov term, which means the time-dependent potential term. And this second term is coming from the collision term. Such difference is the reason why we don't need the theta term in the this first term.
Okay, so it's not it's theta dimensionless.
Dimensionless. Yes. And this is the some collision process. It's cost graining of the collision process give rise to this theta term. But for the Brasov term, we have don't have such process. So this is the
But this would
yes from your relaxation time approximation. Is that right?
Yes.
But does this imply that your spin density would have the same dimension as the vorticity? Because if you compare the left hand side and your right hand side.
Yes. So I just omit the h bar. So in this expression, just I choose the frequency for both the spin and the vorticity.
Okay. Next question is that in one slide you said that when there is the rotational viscosity, the total viscosity will be shifted by mu plus mu rotational. I wonder whether this is true only for incompressible fluid.
Sorry,
for incompressible fluid. Have you used the incompressible condition to derive this equation?
I think so. I've just used the divergence of the V is equal to 0. I use.
Yeah. Okay.
Yes.
Yeah. Okay. Then I understand. Okay. The last question is that you talked about a lot of the Barnett effect. Have you considered or have you tried to detect the inverse Barnett effect, namely the Einstein-Hasse effect, by using your experimental setup?
Yes. Now we are doing such a project, and one demonstration of the Einstein-Hasse effect is this. Okay. So the collaborator demonstrates the Einstein-Hasse effect driven by the spin current injection give rise to the mechanical torque. And this setup is the ferromagnetic insulator cantilever, ferromagnetic insulating the material. And you apply the heat, then the spin wave propagation is generated in the ferromagnetic cantilever. And this spin wave relax, then this spin angular momentum is converted into the mechanical torque, and such mechanical torque is excites the bending motion of the cantilever. Okay? This is the new type of the Einstein-Hasse effect. And also now we consider a variety of the Einstein-Hasse effect. Yeah.
Okay, that's interesting. Okay, thank you.
Yeah, thank you.
Okay, so we still have 2 minutes. So if anybody has any question or comment, if not, I have a question. So you showed some expression that is E is actually somehow corrected by the rotation times R times B. And so my question is that somehow some identified as some really induced genuine electric field, or is that somehow some pseudo electric field felt by only spin, or expression seems that some additional electric field is induced. But my question is that really the electric field felt by the charge, or is it simply the expression?
I think both. This is kind of a real electric field. I mean, this effective electric field is acts on to the electric electron charge as well as the spins. Okay, for the spin sector, actually I omit this expression, but actually we also have the
then maybe so there must be some simple derivation using even in the classical electrodynamics.
Yes.
Okay.
Yeah.
I see. So this is not really a
It's
topological
like Lorentz transformation.
No.
Oh, I see. Okay. Now I see. Thank you very much for the comment. Okay, now I completely understand. Okay, so now it is. So do you have anything to say, Mamoru?
Actually, the JBSJ paper, this is the review for this mechanism, and in this paper, I explicitly show all of the term for the related this electric term. Yeah.
Okay, thank you.
Yeah.
Now, so this is exactly the time. So let's close this session. Thank you very much, Mamoru.